Tic-Tac-Toe is a very simple game. Everybody knows Tic-Tac-Toe. Half the people think it's 3 to the 9. Half the people think it's 9 to the 3. And in Tic-Tac-Toe, you have this little board. Let's draw a Tic-Tac-Toe board. Okay. So a Tic-Tac-Toe board looks like this. Tic-Tac-Toe. And in Tic-Tac-Toe, there's 9 squares, but don't be confused. Just because there's 9 squares doesn't mean there are 9 states. A state is any configuration of these things. So there's 3 choices for this square. It could be O or X or blank. Or this square could be O or X or blank. And this square could be O or X or blank. And so there's 3 choices for every square. There are 9 squares. And when you have independent choices like this, you multiply them. So it's 3 times 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 3, also known as 3 to the power 9. So that's the number of ways you can make a board with X's and O's. Actually, this is a little bit of an overestimate because some of them are not valid positions. Like you can't have all X's, but this is like the right order of magnitude. So 3 to the power 9, which is a lot bigger than 9 to the power 3. So if you said 3 to the power 9, that's the right kind of thing that we're going for. 3 to the power 9. What is 3 to the power 9? 3 to the power 9. It's 20,000. So this is right on the edge of if you were trying to train your neural, like a system to learn this kind of thing, you could make a system with 20,000 states. Like your computer can store 20,000 pieces of information, which means you could just memorize Tic-Tac-Toe. Like you could just write down every position possible and like what to do in that position, and you would be able to figure it out. So Tic-Tac-Toe is right on the edge of what can you solve with the square brackets, V of S, like we were doing last class. And that is why I made a game that is slightly larger than Tic-Tac-Toe that I think is like a little bit too big to solve like this. You're going to have to use what we have been doing. So Tic-Tac-Toe is V of S solvable, barely. But I made a game that's a little bit bigger. And so the game I made is slightly bigger. It is on a 4x4 grid. 4x4 grid. So it looks like this. And so already it would be 3 to the power 16, which is already quite big. But actually you'll see there's more than 3 types of pieces that can happen in this game. And the name of this game is, I think you will like the name. I made up the name and then the rest of the game followed after that. The name of the game is Pig-Tac-Toe. Pig-Tac-Toe. And it is a combination of Pig and Tic-Tac-Toe. You play it on a 4x4 grid, and you don't stop when the first player gets 3 in a line. You keep going. So, I should say why you should care about this game a lot. This game will be your final project for the course. So you'll make an AI that plays Pig-Tac-Toe, and you're going to have to use the stuff with the V of S and figure it out. So actually, Tic-Tac-Toe, the regular Tic-Tac-Toe, will be your assignment 4. That'll be out very soon. And Pig-Tac-Toe will be assignment 5 in the final project working on this. So let me tell you the rules of the game. Players can place X's and O's on a 4x4 grid, and you try to get 3 in a row. So that's the same goal of the game as Tic-Tac-Toe. But unlike Tic-Tac-Toe, the game does not end when the first 3 in a line happens. Instead, the game is played until the board is filled, and any 3 in a line is worth 1 victory point. The player with the most victory points at the end of the game wins. A single X or an O can contribute to multiple victory points. So if you have 4 X's in a row, that's like 2 victory points because of the first 3 and then the second 3. That's the object of the game. How to place the X's and the O's, this is where the pig part of the game comes in. So on a turn, a player does the following 2 things. Step 1, you place a potential X. So you write down where you would like there to be an X, but it's not a real X until step 2, where you can play it safe and bank, or you can take a risk and roll again. If you bank, all your potential X's become real X's. They're permanently added to the board, and then your turn is over. But if you're greedy, you can roll again. And if you choose to roll, you roll a 6-sided dice. On a roll of 3, 4, 5, or 6, then you're successful. You get to place another potential X. You go back to step 1. Now you got 2 pieces going down in 1 turn. Good for you. But if you get a 1 or a 2, all your potential X's are removed, and it's the other player's turn. So it's a combination of Pig and Tic-Tac-Toe on a 4x4 board. There is one special starting rule. It turns out going first in Pig-Tac-Toe is a big advantage. So to kind of offset it, whoever goes second gets a free random square to start the game. And the game goes until it's all filled up, and that is the game. Any questions or comments about the rules of the game? Well, we're going to play around. That's why I opened up the chat. So you guys are going to tell me in the chat, I'm going to play the classroom at Pig-Tac-Toe, and you guys will tell me what you want to do in the chat. So let's label the squares. I guess we'll call these ones A, B, C, D, and we'll call these things 1, 2, 3, 4. So in the chat, you can type in things like A1, A2, or whatever, wherever you want to play, and I will go with like whatever I see the most of. I guess you guys got to decide, do you want to go first or second? So type in the chat first or second if you want to go first or second, and let's see what you're doing. Okay, I'm not sure if this chat thing works. People are yelling at second, first. We got 3 firsts, 2 seconds, 4 firsts. Okay, I think first is winning it. So you guys go first. If you guys go first, I get a random starting square. So to get a random starting square, I'm going to say D16 dice roll. Will that work? Or does it only, oh, here it is. What is this? This is a 12. I want a 16. No, this is a modifier. I don't want that. Okay, we're going to roll a 20, and if it's over 16, we're going to roll again. 20, I got a 6. So the 6th square for me, I get filled in. So I get the 6th square filled in. 1, 2, 3, 4, 5, 6. I get this one. I'll be O. You guys can be X. So I get this one. So the second player gets a random square. I got this O. Now it's your turn. Where do you guys want to play first? Type in the chat the letter and the number of where you want to put your first potential X. Okay. And I guess this is, I got to clear this thing. Okay. Let's see in the chat. What are people saying? Okay, I got a C2. I see a couple people on C2. Lots of people like C2. Okay, C2 is clear winner over here. So you guys get a potential X in C2. I'm going to put it as a little baby X in the corner over there because it's not a real X until you bank it. This is the exciting part of the game. You're going to roll again, get greedy, or you're going to stop and claim your 1X. So type in roll or stop in the chat. If you guys roll again, I'm going to roll the dice. And on a 1 or a 2, you lose all your pieces from the turn. Okay. This is where the fun begins. All right, in the chat, people are saying, roll again, roll. Everyone likes to roll. One voice of reason says stop, but everyone says roll. Okay, you guys are rolling. So here we go. I'm going to roll the dice. I'm going to hit the roll button. On a 1 or a 2, you lose your pieces. On a 3, 4, 5, you get to go again. 4. Okay, so you got it. You guys get to put another one down. So in the chat, where do you want your second potential piece to go? Second potential piece. Where is it going to go? And I got to navigate my tabs here. Second potential piece. Okay, I got a B2 is popular. B2. Can you show the board again quickly? Yes, I can show the board again quickly. Yeah. Here, I can try to have more than one tab open at a time. No, apparently not. Okay. All right. In the chat, B2. I'm seeing B2. Let's do B2. B2. That's here. Okay. Now you guys are going to roll again or stop. This is what you got to decide. Roll or stop. Stop. Ooh, this might be split. Roll. Okay, wait. Stop, roll, stop, roll. Stop, stop, roll, stop. I think slightly more people on stop. I think it's pretty close, but I'm seeing stop. I'm seeing some stop. Okay, very close. We're going to say you stop, which is very wise. Wise choice, very wise. So these X's become real X's. You got the 2 permanent X's, and now it's my turn. I'm going to put my first potential O, I think, here. And I'm going to be greedy. Let's roll it. Let's do it. I'm rolling. Let's do it. We're rolling. If I get a 1 or a 2, I'm going to get removed. 5. Okay, I got it. And then I'm going to put my second O up here, and I'm going to bank. I'm stopping there. So I get two big O's, and I have scored my first victory point of the game with 3 in a row. It's your turn to play. Where do you guys want it? I have a suspicion of what you might want to do here. Let's see. Let's see what it's going to be. D2. Oh, what a surprise. Okay, D2. Very nice play. This is the exciting part. You guys gonna bank that on a measly 1 banker, or are you gonna go for 2? Let's find out in the chat. Roll or stop. All right. Roll for show. Okay. Wow. Okay, everyone wants to roll. You guys, that's very greedy. Very greedy. Ah! So you lose. You lose your piece. It is cast into the abyss. And as my turn, I get a little potential. Oh, I'm happy with just 1. I'll take 1 there. Yeah, that's fine with me. No problem. Nice O over there. Okay, your turn. You guys get your first one. Where are you going to place it? Where on the board do you want your first O, or your next X? Okay. What do we got? C. Oh. Wait, I got to go to the bottom. Okay. B1, C1, C3, C3. C3. I'm seeing C3. Let's go through C3. C3. Ooh, very nice. Okay. Roll or stop. Roll or stop. Roll, 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 roll. Wow. You guys are very greedy. Okay. Here we go. Rolling. 4. Okay, you got it. Where's the next one going to go? Let me open up the thing. Where do you want the next one? The next piece should be which one? Okay. C1, I'm seeing C1 and A1. Okay, slightly more C1s. C1s. I think I'm seeing C1. 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 Okay, and you're going to roll or you're going to stop? Roll or stop? Stop, stop, stop. Stop, stop, stop. Everybody, wow, you guys, a hive mind. You're stopping here on your C1. Very nice. Very nice play. Okay, my turn. I'm going to put my first potential guy down here in the corner on A1. No, actually, no, I'm not going to do that. This is a lie. I'm going to do D4. D4. Here we go. D4. D4. And I'm going to roll. I'm going to roll again on that. Do I want to roll again? Yeah, let's roll again on that. Let's roll. As you know, the people at Google can hear you. All right. Okay. And then I think I'm going to go here. And I'm going to stop. So I'm going to bank this one and this one for the sandwich. Is your turn. Where do you guys want to play your thing? Was there a hand or a question? No? Okay. Where do you want to play your first potential piece? A3. I'm seeing A3 and D3. A3, D3. A3, 2 A3s. A3, A3. A3 is the winner. We're going to go A3. A3. A3 is up here. A3, very nice. And then do you want to roll again or roll or bank? Roll or bank. Roll, roll, roll. Everyone wants to roll. All right, here we go. 5. You succeeded. Where should you place your next piece? Where do you want your next piece to go? Okay, D3, I'm seeing D3. D3 is very popular. Okay, roll again or stop after D3. D3 is this one. Okay, D3. Roll again or stop. And people are saying, ooh, it's a mix. Roll, roll, roll. Roll, roll, stop. Roll, roll, roll. Okay, I'm seeing a roll. You're rolling. Oh! All right, so this goes away, and this one goes away. All right, my turn here. Let's see. I'll take this one and stop, please. I'll take this and stop right away. No rolling for me. I'll take that. Okay, your turn. Where do you want the next piece? B2. I'm seeing a B2. B4, B2, A4, A4. Ooh, it's all over the place. I think A4 is the first one. A4 only got 2 votes, but I think that's the best one. Yeah, you guys are in trouble here. Okay, A4. Okay, and then roll or stop. I think I know what you're going to do. Let's see. Roll or stop. Roll, roll, roll. Everybody wants to roll. Yeah, okay. We're rolling. 3. Okay, you got it. So where do you want to place your next piece? You got the little guy in A4. Where do you want the next one? This one. B4, B1, 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 B1. I'm seeing B1s. Let's go B1. B1. And then you got to decide, do you want to roll again or stop? Oh, that's B4. My mistake. Thank you. Thank you. Indexing the wrong way. Okay. B1. Very nice B1. Okay. Roll or stop. Ooh, people want to roll. Out for blood. Okay. Here we go. Rolling. 2. Oh, no. Yes. I told the people at Google to rig the dice rolls before the class. Okay, so where do I want to go? I think I'm going to take another little one banker here. Let's see. I can block this. I think I'll take this one and then I'll stop. Yeah, let's do that. All right. Your turn again. Where is it going to be? Can you guys even win at this point? Let me see. All right, let's call it a game then. So I have 1, 2, 3 victory points. You guys have a measly 1, maybe potentially a second 2. But that's it. So I win the game. All right. So the point of this project is you got to beat me, okay, guys? So we're gonna write an AI program that beats everybody at this game. So those are the rules. Some other project details. So it's going to be like pretty open-ended. So I'm going to give you this code that like runs the game and like sets you up. You're going to write a specific AI that does a specific thing that's going to use the value functions v. You can work with a partner if you want. If you do work with a partner, I'm going to have like a slightly higher expectation of what you're doing. There's going to be some benchmark AIs on Gradescope, so you can submit your AI to Gradescope and see like how well you're doing. So I'm beating the really bad AI 80% of the time. I'm beating the medium AI 40% of the time, and so on. And then maybe at the end, I'll do like a little final tournament where everybody plays each other. So that'll be fun. I'll tell you how the code works. Today, in the actual lecture today, we're gonna work on Tic-Tac-Toe, and it's gonna use a lot of the same code because this is basically the same thing as Tic-Tac-Toe. And eventually, we're gonna get to some versions of this where it can run extremely fast. So I was doing this last night. It ran 100,000 simulations of Pig-Tac-Toe. Guess how long it took to run 100,000 games? 10 seconds. It took 13 seconds. So it's really highly efficient, and we're going to learn how to do this stuff so you guys can have some efficient code as well and like run a lot of simulations that'll help your Monte Carlo solutions get better and better faster. And I'll show you, we're going to have we're going to build up from the Tic-Tac-Toe AI, and then you'll be able to do whatever you want on this one and have fun with it. Any questions or comments about the vague ideas? I'll post some stuff with it this weekend. That'll be up there for you to read, but that is what the project will be. Questions, comments? Okay, so to start with, we're starting with Tic-Tac-Toe today. And Tic-Tac-Toe is just barely the right size, where you could solve it with the square brackets. So Tic-Tac-Toe has 3 to the 9. Pig-Tac-Toe has something at least like 4 to the power 16. Oh boy. So Pig-Tac-Toe is a lot bigger because there's 16 squares, and you have this issue of the permanent things and the like temporary things, so it's a lot harder to solve. I don't think you could solve Pig-Tac-Toe with a v square bracket s, and that's why we're going to learn how to do it with parameters. So v of s, comma, theta, where theta are the parameters, just like we were doing last class. Okay, and the first little warm-up question for you on how the parameters work is, what would happen in this very simple situation? So here's a situation. We have some kind of situation. We have n states, S1, S2, all the way to Sn. And we are thinking, let's just use one parameter per state. So we got theta, it's a vector. It's got theta 1, theta 2, all the way to theta n. And we just make the value function v of s comma theta. It's theta 1 if you're in state 1. It's theta 2 if you're in state 2. It's theta 3 if you're in state 3. Very nice function. Very simple. And the question is, what is going on with the gradient in this case? So the gradient is what we learned last class is going to help us do these kinds of things. And I think if you understand this simple example, it'll help you sort of learn how this gradient descent thing works. So I'm going to give you 2 minutes to try to puzzle this out. You might have to remember what is the definition of the gradient, and we'll go from there. Okay, I'm going to give you if you still need to work on it, you can work on it for a second. Let me do a quick little recap, a little review from last class while I give people an extra minute. So what did we do last class? Last class we were using gradient descent to fit a data set. So this was last class. We did gradient descent to fit a data set, which is the same kind of thing you do in stats class. I guess in stats class, you don't always use gradient descent. You sometimes use other methods like some matrix stuff or whatever. But in this class, we're going to do everything with gradient descent. And the whole secret was we defined this loss function. So we had the loss function. It was like how bad you're doing. So how good or bad are these parameters? That's what the loss function measures. And the loss function is equal to, you take the function that you currently have, you plug in the x values at the parameters you have, and you compare that to the y values they're supposed to be. So f of xi is supposed to be exactly equal to yi. In real life, we're close but not equal, so we subtract them, and then we square it. This is the square loss function. And we often, in real life, do the mean squared error, so the loss is the sum over the number of data points, and you divide by the number of data points. So this was what we did last class. And then we minimized it with gradient descent. And to minimize it with gradient descent, you do the gradient. So you do the gradient of the loss, and that is going to be like a vector of all the partial derivatives. You can do this one by hand. It's going to depend on something. 1 to the n data. You're going to have f of xi semicolon theta minus yi, and then you're going to have the gradient of f of xi. Sticking on over here. Oh, I guess there's a 2. There should be a 2. Sometimes you will define the mean squared error with 1/2 to cancel out the 2, but I didn't do that, so there's a 2. And so the question I asked you in Mathematize was sort of to please tell me about this this term over here. What does the gradient look like? Okay, so that was last class. Any follow-up sort of questions from the lecture last class about gradient descent? Okay, let's see what you guys said. What's going on in this gradient? I gave you a very specific situation where the gradient is going to take a specific form. Okay, so I want to go back here, and I want to see what you said. You said, okay, So we're doing at the s equals s2. The gradient is always a vector. It's the vector of all the partial derivatives. So the partial derivative with respect to theta 1, with respect to theta 2, and so on. And we're at the state s equals s2, and theta equals these decimals of pi. Okay. The first entry, 10 people said was 0. The second entry, 10 people said was 0, and 5 people said was 1. Some people said was -1. The next entry, 10 people said was 0, and 11 people said this one is 0. 4 people said it's 8. So the most common answer in all cases was 0. 0, 0, 0, 0, 0, 0. Okay. I'll tell you, it is not all zeros. There is something here that is not 0. It's not all zeros. So at least one of these boxes has a 0, maybe more than one. So let me remind you what is the gradient. Maybe this will help. The gradient it's the vector of all the partial derivatives. The gradient of f of x theta, it is the vector partial theta 1 of f, partial theta 2 of f, partial theta 3 of f, and so on, all the way up to partial theta n of f. Okay, so it's a vector, it's got n components, where the n components are the n theta values. How is f changing when you change theta 1? How is f changing when you change theta 2? That kind of thing. So let's do a revote on this one and try to figure out which of these 4 boxes is non-zero. Okay, I'm gonna revote it. Let's revote it. Here we go. Repeat. Parameter says v2. Okay, it's open. I'll give you another 2 minutes. All right, 30 seconds left to put in your updated guess. Okay, let's see what you said this time. They're not all 0. Which ones are not 0? The first entry, now 17 people on 0. That is correct. This first entry is 0. What about the second entry? The second entry, 16 people are on 1. Amazing switch. What about the rest? 0, 0, 0. You guys all got it this time. Amazing work. Great job. So the correct answer is 0, 1, 0, 0, 0. This, when you plug in S2, the only value is theta 2. So the function is equal to theta 2 when s equals s2. You can kind of see this is a function with 2 inputs, right? And the s's are fixed. So we're not doing the derivative with respect to s or anything. In fact, it doesn't even make sense to do the derivative with respect to s. It's some discrete set. It's the thetas we're talking about. And when s equals s2, it's just the function theta 2. So I was really asking you, please do the derivative of theta 2. And the answer is, it's the vector, which is all zeros except for a 1 in the second component. So let's see what would this look like in our gradient descent formula over here. So if we do a gradient descent step, And we know in this special case what the f is. Let's do it. And I guess I'll write it with a v. So because we're doing value functions. So value functions. Ooh, this is the chonky boy. Okay, here we go. Value functions. V of s comma theta. So our x's, the x's from stats class, those are the states. And the y's from stats class, those are the g's, right? Those are the expected value of the total return that we want to get. So I guess they're the expected g's. That's what we really want. But our value function v is supposed to match the value of the expected value started from any state. S0 equals s. Okay, great. And if we do this gradient step, so what is the gradient of the loss? If we plug it in here, what it is, okay, I'm not going to write the sum part. It is equal to the value function v of s comma theta. Let's put in s equals s2, like in the example. So the value function s2 minus the y value, that's the true, let's say the true average, g of s0 equals s2 times the gradient. The gradient, that is what you just calculated in Mathematize, v of s2. So that's the gradient of the loss. It's the difference between the value function and the actual expected total return multiplied by this gradient. What does it look like when we do a step of gradient descent? So gradient descent says, please let, is this bigger or not? Okay. The gradient descent says theta equals the old theta, the new theta equals the old theta, plus alpha times the gradient of the loss. Actually, this is completely wrong. This is gradient ascent. This is going up, making the loss bigger. We want to make the loss smaller, so we should subtract. So let's subtract. Minus. Okay. So what would this look like? Well, I would take the vector of all the theta, so theta 1, theta 2, theta 3, dot, 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 theta n. And it would be whatever it was before, theta 1, theta 2, theta 3, dot, 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 all the way up to theta n. And then I subtract off alpha times this difference, v of s2 semicolon theta, minus whatever the true value is over here, g of s0 equals s2. And then I do the vector that you guys told me, which is 0, 1, 0, dot, 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 all the way down to 0. So the gradient in this case is a vector of all zeros, except for it has a 1 in the second component, and that's because s equals s2. So that was why this thing is a 1. Okay, what is this update rule doing? We're updating scaled by this amount, but it's a vector which is 0 and then 1 and then all zeros. So which of the thetas are going to get updated? The only one that's going to get updated is theta 2. Theta 2. All these other things, they're just like doing nothing, right? Theta 3 is theta 3 well, minus 0. Theta 4 is theta 4 minus 0. Like nothing changes except for theta 2. So the only non-trivial change in this situation is theta 2 equals the new value is the old value minus alpha times v of s2 theta minus whatever it's supposed to be, g of s0 equals s2, and then times 1, times 1. So the gradient was 1. And what this is saying is, look, if v is currently above the value of e, right, if this thing is a positive number in brackets over here, if whatever we think the value of v is, if that is larger than what it's supposed to be, then we're saying bump theta 2 down, right? If this value is like positive if we're currently overestimating, positive when v of s2 theta 2 is too large. Too large. By the way, v of s2 theta, there's a name for that. That's theta 2. Why don't I write that everywhere? Let's write that everywhere. This is equal to v of s2 theta, right? Because the v function is just the value at the state s2 is theta 2. So when it's too big, we're like, push it down a bit, cool it off, subtract a little bit. When we're overestimating, we gotta make it a little bit smaller. What about when we're underestimating? Well, this is a negative value the other way. When I'll say theta 2 is too small. So on the other hand, if theta 2 is too small, then we bump it up a little bit. Do you guys recognize this update rule from earlier in the course? This is exactly the same update rule as the constant alpha averaging, except instead of writing v of square bracket, like before I would write v of square bracket s2, and I would say it's equal to v of square bracket s2 minus alpha v of square bracket s2 minus g times 1. That's what we were doing before. So this is exactly the constant alpha update rule, except for the thetas are getting updated rather than the v's. And that's because in this simple example, the thetas and the v's are like exactly the same thing. The parameters theta are exactly the values of v. So you can kind of think of everything we're doing is like a generalization to situations where the gradient is sometimes something other than a 1 and all zeros, right? So kind of in this very simple example, you're in state S2. Which parameters are involved in state S2? Well, it's only theta 2. In general, a bunch of parameters might be involved. So the next simplest example, this is the simplest possible example. Here is the next simplest example that I'm going to do. So the next simplest example, let's do a situation where v of theta, of s comma theta, it is not just, there's the theta value doesn't control just one state at a time. Now each theta value controls a whole group of states. So I'm going to do it like this. I'm going to do theta 1 for s values in some group. So if s is in the first group of states, what letter should I use for group? Let's do A. A is a nice letter. A1. No, A is actions. Oh no, this is a big disaster. I can't do S for set because S is state. Let's see, C for collection. Let's call them the collections. C1. Okay, so there's some group of states, and I group them all together, and theta 1 is in charge of everybody inside that collection. And theta 2 is in charge of everybody inside the next collection of states, and so on. S in C2, and dot, 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 plus theta n. Okay, this is important. The theta n will be different now. So the theta times the number of parameters times the indicator of S in C of number of parameters. So instead of doing each individual state, each theta is in charge of some collection of states. And the collections, they can just be like any arbitrary collection. I'll show you a picture of what this looks like. And it's a very nice picture from the textbook. Let me show you the picture. In the textbook, it's called Coarse Coding. So this is the chapter we're doing. And you should think of, this is the picture that I have in my mind. So imagine all the points on the xy plane here are states S. And the little circles represent these collections. So this is maybe C1, this is C2, this is C3, this is C4, and so on. And for some value, some particular state S, like what about this value of S right here? Which collections is it in? It's in the states that overlap with it. So it's in this collection here, it's in this collection here, it's in this collection here. It's in 3 different collections. Okay? And what we're saying is, if we want to know the value at the state S, we have 3 parameters, 3 theta values that correspond to these 3 circles, and the value of the function S should be the sum of the theta values at those points. Is the picture making sense and the equation? Now let's ask a question. What is the gradient? The gradient we did before, what is the gradient of this S value? So that's the picture. Here is the question. Now let's do the gradient. So the gradient with respect to theta of V of S theta, what is it now? Well, so for some fixed S, so let's say for some fixed S. For some S, fixed S. So don't get mixed up between the S's and the thetas. For some fixed S, we do the gradient. Well, this will be 0. We'll have a bunch of zeros, just like last time. Anytime the S is, this indicator function of S being in one of the collections, when that is 0, the theta doesn't play. But if S is in the collection, then it's just like last time, you have the theta there. So I claim it's going to be the following vector. It's going to be a vector of all zeros, 0, 0, 0, except for it's going to have 1s, exactly, collections where S is in the collection. In the collection number, let's call it K. So it has a 1 in entry K when the state is in this collection. And so I'm going to draw, in my little example, I'm going to draw 3 of them as being 1 and the rest being all zeros. So it's all zeros except for 3 1s. Why did I draw 3? I wanted to match the picture. So here is the situation. There are 3 non-zero things because S is in 3 things. So now what would happen in this example, we're using this value function parameterization of using a bunch of collections. What happens in the gradient step, right? So let's go back to this gradient step like we did before. So the gradient update, before, we were only updating one. We were updating just one entry, just the theta 2 value. But now we will update 3 at a time, right? And I think the best way to imagine it is the picture. Like, what's going to happen is we're going to run our simulation starting from the state S. We're going to see what happens. And then at the end, we're going to get a value. We're going to say, look, either it was an underestimate or an overestimate. If it was an underestimate, we need to bump up the value here. How are we going to bump up the value? Well, we're going to bump up the theta values for all 3 circles. All 3 circles get bumped up. If it's an overestimate, we bump down all 3 circles. So it's kind of a generalization of what we did before. What we did before was doing one state at a time, but now we're doing entire collections at a time, right? Because when we change the theta value for a circle, every single value inside that circle gets changed. So this gets bumped up and down as before. The picture is trying to show you why this is a good idea. Why is this a good idea? Let me do the example of tic-tac-toe, and we'll go back to the picture in a second. So it really is the difference between learning one state at a time, learn one state at a time, versus learn many states at a time. And let's do a tic-tac-toe example. That'll be the code example that I'll show you in a minute as well. So here is a little tic-tac-toe situation. Let's say it's X's turn here, and X realizes if I go here, I win the game. So X is like, hey, I win the game. This is wonderful, wonderful news. We're happy. Yay. Okay. If we're learning one state at a time, then the state is literally this exact configurations of X's and O's. So if we're learning one state at a time, then we're saying next time you see the exact configuration of X, X, O, O, that's a good state. We should do that. But instead, we can learn many states at a time. So let's let the collection, let's let C be the collection of all states with X, X, blank. So I'm going to draw it like this. There's going to be X, X, and blank, and then I don't care what's anywhere else. These can be literally anything, right? So there's sort of like 3 options for each of these blanks. This is a collection of 3 to the power 1, 2, 3, 4, 5, 6. There's 3 to the power 6 states in this collection, and they are all the states that have an X and an X and a blank. And all of them, I'm saying, you can group all those together. If you see this any time, that's always good for us, right? Because we always get our 3 in a row. And so what this is doing is instead of learning one point at a time and having like 20,000 states we got to go through, we can learn in groups of 3 to the 6 and only have like 27 groups that we need to go through. And that's what they're trying to show you in the picture from the textbook as well. So they're saying if you learn something about one state S and you're in a state S prime that is nearby it, what does nearby mean? Nearby means it's in some of the same collections. So S prime in my tic-tac-toe example, if this was the exact state S right here, then state S prime nearby, it might be like, oh, replace this O with an O there, right? It's still very close in the sense that they're both in the same collection. And if we learn about one set, we learn this is really good, we boost up the value of the value function here, then we know that this one is good too. So we kind of generalize our knowledge. That's what is being shown in the picture over here. So coarse coding, generalizations from state S to S prime, depends on the number of their features in common, how many times they overlap. And so this is the secret to scaling up to really big state spaces. You can't learn one state at a time. You got to use the parameters and then have much fewer parameters than there are states, and then use this generalization idea to generalize from one state to the other state. That's the idea, and this is like sort of the math of how it works with the gradients. So you can kind of see like what is the gradient doing, and you can see where that formula sort of came from. I'm going to show you in code in 1 second how it actually works as well. But this is a great place to stop for questions. Yeah?
Is it useful to use the topological information from the state space?
I think if you know something about the state space, what you want to do is you want to bake that in to how you parameterize the function. So a really good example actually is this picture, right? So in this picture, I said the states are X and Y coordinates at a point, right? And by using these circles, I'm sort of implicitly assuming that when 2 points are close together, that means that they like represent similar things, similar outcomes right? And in a lot of situations, that's like absolutely true. So if that's a situation where similar x and y values lead to similar things in the sense of like Euclidean distance, then the circles make sense. Actually, if I scroll down to the bottom of this page, they have an example over here. They call this one asymmetric. Maybe you want to draw the circles like this. And if you draw the circles like this, what you're saying is, look, if you're close in the x coordinates, that's not as important as being close in the y coordinates, right? And so if you have some like outside information about what close or not close means, you can bake that into your sets and like get an advantage that way because it'll generalize better. So if you have something like topological information, you can include that in your value function in like an appropriate way.
It's not actually the state space that really matters.
I guess it's like the thing that really matters, right, is which states lead to which outcomes in the Markov reward process. And what you would like to do is you would like to group together states that have similar outcomes. You would like to group those states together as being similar in the value function so that you can learn, if you learn about one, you automatically learn about the other. Yeah, that's a great point. Yeah?
How do you determine which states belong to the same collection as each other? Like,
Yeah.
for example, how do you know a state that is in the circle and the nearby one is outside of it?
Yes, right. So somebody has to come along and say, these are the collections I'm looking at. So the job of the person who makes the value function is to come up with how do I go from parameters to the value? And they have to put in whatever they want the function to be. And if they're going to do it this way, they have to define what the collections are. Yeah, this is a great, absolutely fantastic question. I'm going to show you in the Tic-Tac-Toe what I did. And then you guys are going to do something similar for assignment 4 as well. Yeah. Yeah, great. Any other questions? Okay, so let me tell you what I did. I did this exact situation with this exact example in the Tic-Tac-Toe. So I made collections that look literally like this kind of collection. And I'm going to show you how it worked and how it worked in the Monte Carlo. Oh, maybe one thing that I didn't quite say. Maybe I should, okay, I'll just bring up the code. So this is the algorithm we're using. So it's still a Monte Carlo algorithm, just like we were doing before, but now it uses gradient descent. And the little one-liner over here, this is the code, right? So this is the difference between V and G. G is like what you observe in your simulation. Of course, we actually want V to be equal to the average of G, but we don't know the average of G. We just use individual samples. And this is exactly what I showed you guys before. So you take the difference, is V an overestimate or an underestimate, and you scale it by the gradient that tells you sort of which parameters to update and by how much. And we're trying to boost the value of V to be equal to G. So if it's too small, make it bigger. If it's too big, make it smaller. You might notice it's backwards to what I wrote. I wrote V minus G. They wrote G minus V. Who is right? Yeah.
It doesn't matter because they put a plus in front of it.
Yeah, that's right. Yeah. So I wrote it the other way, but they put a plus. I think it makes a lot more sense to put a minus because we're doing gradient descent. You want to go down the hill, and when you do gradient descent, you got to put a minus to go down the hill. The reason, obviously it's mathematically the same. The reason that they have a minus here is there's also another minus. Like when you do the gradient of G minus V squared, you're getting a minus the gradient. So however you want to do it is fine, but just make sure you don't get bamboozled by the minus signs. Okay, let me show you the Tic-Tac-Toe example. So this is the Tic-Tac-Toe Monte Carlo thing. It has a lot of the same functions as the Pig-Tac-Toe that you guys were going to be doing. One function that you will never have to look at, except it might be good to know what it does, is a function called create k-in-a-lines. And what this does, it makes all possible 3x3 things of length 3. So at the end of the day, it will make something of length 8. Actually, why don't I just run it? Let's run it and output what it says. Okay, the hardest part is importing everything. All right. Yeah, I don't think I need every single one of these, but okay. So okay, create k-in-a-lines, and then let's do it. So in Tic-Tac-Toe, the 3-in-a-lines are actually the ways you win, right? So let me run that. Rows is not defined. Okay, I gotta make some rows. Okay, let's run this one and then run that one. Okay. So yeah, this might be a little bit more tedious than it needs to be, but it'll be also useful for you for your final project to see what this is. So what is all possible wins? It's an array. Let's print its shape. Yeah, let's do that. That's great. Dot shape. Let's say no. Okay. Okay. Try again. So it's a 3x3 by 8 right? So 3 by 3 represents the 3 by 3 grid you get in tic-tac-toe, and there's 8 of them. So if I do this thing like this, colon, comma, 0, it'll give me the 0th way to win. This is one way to win in tic-tac-toe. There's 3 pieces on the top, and then everything else is nothing, right? That's the 0th way to win. The first way to win is like this, true, true, true in the middle. What's the second way to win? So there's 8 ways to win in tic-tac-toe, corresponding to these 8 ways. Okay, and the way this code works is it uses this array of 3 by 3 by 8 to check if you're going to win. Because it does has win, which does some fancy shenanigans with axes to check all the possible ways all at once. So you give it a board, and it checks every single one at the same time using these array operations. We're going to talk more about these later on. Okay, and then this is where I'm using these kinds of things to calculate my value function. So this is the value function, and this value function is exactly like these collections that I had before. Let's ignore these ones that are in like this. Okay, so what are they? So first of all, I calculate where could player 1 potentially go? Where could player 1 potentially go? And player 1 can potentially go on places where they already have an X and places that are empty. So that's what this line does. It's saying, where could player 1 potentially go? And basically, it's excluding anywhere that player 2 has already gone. So this player 1 potential, it inputs the board. The board is an array of integers. So the board looks like this. And it's got ones, x equals 1, empty equals 0, and O equals 2. And so the board maybe looks like this, like x, x, O, O. And what the potential thing does, it says take all the ones that are either empty or have an x. So the player 1 potentials is this set of points, and it inputs that as an array. So it's an array of 3 by 3 with trues and falses on where it is. And then I calculate with this little command, player 1 3 in a lines. What it does is it calculates all the possible ways that you could win. And so what it's saying is this little player 1 potential, it includes, in my example, it includes 3 little lines. It includes this line and this line. So of the 8 possible ways to win, there's only 2 of them left in my potentials. So my potentials, the player 1 potentials, it gets mapped to this vector. It's got all zeros, except it's got a 1 in 2 spots for these two ways. So that way to win and that way to win are both a 1.
What did you have 3 from the horizontal?
Oh, I forgot the horizontal one. Yes, okay. So programming good, tic-tac-toe less good. Okay, there you go. So there we go. Three ways to win. Thank you. Okay. And then what I did is I assigned a parameter to each of these 3 ways. So the coarse coding, right? The set that includes all these diagonals, that's the collection we were talking about before. And this particular state of having an x here and nothing here and 2 O's here, it's in 3 of these collections. It's in the collection for this diagonal line, the collection for this diagonal line, and the collection for that diagonal line. I made 8 parameters to go with these 8 collections. And that is done at the bottom of the function over here. So the bottom of the function over here is doing this. It does the dot product of the first 8 parameters, and it adds them up. So it says parameters 0 to 8 plus multiply them by the player 1 potential 3 in the lines. There's 8 of those, and you have 8 parameters to go with them. So I'm doing this linear combination and adding them up. So this goes to theta sub diagonal like that, plus theta sub, the middle one, plus theta sub the last horizontal one. Let me draw the board here so you can see what it is. The middle one and the last diagonal line. So there's 8 parameters for these 8 different ways to win, and I'm adding them up because I'm in 3 of them. That's the value of what's going on. So that is the heart of the thing, and it's exactly like I described. It's a kind of a coarse coding where I'm grouping together all the states that have the same potential 3 in a lines. So that's player 1 potentials. You might notice, if you are a shrewd observer of the blackboard, you might notice there's more stuff. What is the rest of the stuff? Well, there's the player 2 potential 3 in a lines, 8 to 16. So I do the same thing, but with the opposite player. So instead of doing it just for the x's, I also do it for the o's. So that is the same kind of situation. In this particular example, in this particular state, the player 2 potentials is all this stuff, right? It's this and this. And so the player 2 potentials are going to be some completely other thing it's going to be like this one. Oh, always getting flummoxed by that one. Okay, this one, and I guess that's it. Okay, so those are where player 2 could win, right? So they have 2 out of the 8 set, and they have 2 more parameters coming up for that. There is one other one that you might notice at the bottom here. There's one other one, which is the player 1 actuals. And this is like if you actually have 3 X's in a row on the board, where is that? And so it just takes the actual places that you have, board equals 1, and it's doing this, calculate all the things with the mask. And the reason I need this one is because when my algorithm decides what to do, it doesn't actually input a state and then decide what to do from there. It inputs all the possible states. So my actual algorithm runs like this. So note, actual algorithm is fed potential states. Potential states. So to give you an example, if the state is like this, x, blank, and then I said, what did I say? O here and O here, O here and O here, then actually this will get split off into, I think, 5 universes, 1, 2, 3, 4, 5, where I play in all the possible spots. X, O, O. That one's exciting. X, O, O. X, O, O. X, O, O. And last but not least, X, O, O. So there's some code that takes state and it calculates all the possible moves, and those are fed into the value function. And this is the equivalent of Q learning versus V learning. So these, technically I should be doing Q of state, comma, action, but we know the rules of tic-tac-toe. We know if we're in a particular state and we play a particular action, this is effectively equal to the value of, in some sense, state plus action, where plus means like add it to the board, right? So instead of saying I'm in this state, which action should I do? What I'm saying is, if you were in that state, would you prefer to be in this one or this one? And so that's a little bit easier. It's going to be the same exact code in your Pig-Tac-Toe, so that makes your job a little bit easier. You never have to deal with Q values for the final project. You only ever have to deal with V's. Okay, wait, that's a lie, because you have to decide whether to roll again or stop. So that'll be like a Q roll and a Q stop, but you can do it with values. So the value function, as I wrote it on the board, or as I wrote it in the program, this value function, it is called on all these states simultaneously. So if I'm in the state, I'm like, what should I do next? I spin off all these potential moves. So this move, this move, this move, this move, and this move, they all go into the value function. They all get a score. So maybe like, if life is good, this one will get the highest score. Maybe this was like, oh, you're definitely going to win, 1.0. This one is like, we're probably going to win, 0.8. This one is like, oh, maybe 0.7. This one is like 0.85, and this one is 0.6. And then we pick the highest one. So the value function kind of rates all the possibilities, and then you want to play the best possible move, so we would choose this one. Okay, that is the hope and the dream. Any questions or comments about the rough idea of how this thing is set up? Okay, and again, you're going to have to get into this in the project in the homeworks. Okay, let's see what happens next. So that's the value function, and then I do the gradient because I'm going to need that later. This is a little function that prints it out nicely. This is a random move player. I trained my computer algorithm to beat the random move thing. Okay? You'll be very impressed to know that I'm quite good at beating someone who plays randomly in tic-tac-toe. Okay, then there's some other, there's some functions like apply actions and stuff. But the meat of the thing is this little loop that just plays tic-tac-toe. And it plays tic-tac-toe, and it learns over time. Is there a plot? Oh, there's no plot. Okay, let's run everything again. And hopefully it will work. Run all. Okay. Okay, might take a minute or two. Okay, let me show you this loop. So, okay, let's do this and try it again. Okay, let me talk to you through this loop while it's doing its thing and learning. I guess let's make sure it's learning. Is there a little slider going up? Board is random. We want this to go up. Okay, great. Okay, it's playing. So let me tell you what it's doing while it's running. So it's literally playing through tic-tac-toe. So we go through turns. There's 2 players. There's player turn equals 1 or player turns equal 2. I get all the possible moves from the current board. And then if you want to, you can print it out. But then what it does is it picks a move. And it's going to either pick the best possible move or it's going to pick a move at random. Do you guys recognize this little algorithm over here, right? So the problem is if you always pick the best possible move, you won't see a lot of situations. So this is a little epsilon greedy schedule where for the first half of the games I play, I pick a random move 25% of the time. And for the second half of the games I play, I only pick a random move 1% of the time. And so I'm kind of being super greedy in the second half. We're hoping things improve there. So if I picked a random move, then I pick a random move. Otherwise, I pick the best possible move. And how do you pick the best possible move? Well, you do the argmax of all the values. So which of those values was the best? And then I'm writing down the states as I go. So I write down all these states. And so I play through a whole round like that. And again, it's me versus me with my little AI brain versus Mr. Random, who always plays random moves. Not very good at Connect 4, or Tic-Tac-Toe rather. Okay, and then at the end of the game, I figure out who won. So the reward, either we won or the opponent won, who has the win. And then what I do is this is the learning part. And this is the gradient descent part. I go through all the states that I saw. So in my game, all the situations that I saw, and I update the parameters according to that formula that we had before. I guess I should have written it with the bracket over here, but it's minus equal alpha times the gradient times the value minus the reward. So this is the underestimate or overestimate, and this is the direction that we're changing. In this particular situation, the gradient of the value is exactly 1s and 0s of the states we're in, of the collections we're in rather. So that is updating the parameters, and then I do it again, and I do the whole thing 400 times. So I do it 400 times, and at the end I got all these parameters. These are the parameters. And they have an interpretation, maybe I'll say that in a second. But here is the plot, here's the exciting plot of how we did in the game. So this is the cumulative reward. -1 means we lost the game, +1 means we won the game, 0 is a tie. So you can see for the first 50 episodes, we were doing quite bad. We were losing about as often as we were winning. But then around episode 50, we mostly figured it out. You'll see we're still doing some ties. Occasionally we're losing. But then things get quite good around episode 200. Does anyone remember what happened around episode 200? Yeah. That's right. Well, we started being greedy more often. We went from being greedy 75% of the time to being greedy 99% of the time. Yeah, so that's exactly right. We started being more greedy, and then we really started to do quite well. By the end of all this, we're really doing quite good. I think I have a little example game printed out over here. Oh, I wrote out these are the values of the theta for the potentials of my potentials and my opponent potentials. These are the actual 3s in a row. You can see some of these values are quite large. Like I really like this one. This is 1.14. If I have a 3 in a row, I should always take it. The fact that some of these are negative is truly bizarre. I don't know why it's doing that. The opponents, those should all be negative. Like the more room the opponent has, the more negative it should be. We haven't figured that out yet. So very funny. But here is a potential game. Here's a run through of a game. So if you set verbose equals true, it runs through the game for you. So the game started the usual way. We moved up here. These are the possible moves we could do. So we're like, should we do this? Value 0.51. Should we do this one? Value 0.59. Should we do this one? Value 0.37. Not so good. Ooh, 0.89. We think if we play here, we're going to win 90% of games. If we play in the middle, we only win 55% of the games. So obviously, this is not very good at tic-tac-toe yet. But, it thinks the best move is to play in the corner. If you play in the corner, you win 102% of the games. Amazing. Yeah.
Scroll up again.
Yes. Yes.
Just keep going. Okay. Interesting.
Yes, right? So, okay.
And when should all the corners be the same? Because it's just, we don't, if you really think about it, we have,
Yeah.
it's just.
Well, think about the way
Yeah.
I implemented it, though. So I have a different parameter for every single line, and the line on the left is a different than the line on the right. It would be very clever if you would come along and say, actually, all the left horizontal line and the right horizontal line, those should have the same parameter. So this is called parameter sharing, and you could say instead of having 8 parameters, you actually have a lot fewer. If you learn something about the right side of the board, you should automatically learn on the left side of the board. Exactly, yeah. So if you know the game has symmetry, you can imbue that into your value function.
Yeah.
I have not done that. Yeah.
You only need position to be the center.
Right. Well, the center is unique. I think the 4 sides are unique and the 4 corners are unique. So I think there's like 3 effective positions for the first one.
Like I guess.
Anyway.
Yeah, I feel like this, like sides and corners, like each should have their own. Like,
Right.
Be the same.
Yes. So there's lots of ways you can do this. Yeah. Okay. Great. Yeah, that's a potential thing you can do for your final project. Okay. Amazing. Great. So I chose to play in the corner because I like that the best. The X's play randomly. The X played over here, and then I'm like, okay, what am I gonna do? I'm gonna find the best move. Let's see, what's the best move? I think the best move is to play next to over here. All right, and that has a 0.867, is quite a bit higher than the other ones. And then I played there, but the X, who's playing randomly, blocked me. Oh no. A lot of the times I will just win the game immediately, but in this situation I didn't. So let's see what I did next. What was my favorite move over here? Best move. Oh, in the top, apparently. The top middle. See, I think the top middle is the best. The truth is, because the other guy is playing randomly, anything that gives me a potential 3 in a row is about as good as the other one. Now let's see if we find the win. This will be embarrassing if we don't. Okay. 0.468, 0.24, 0.75, best move. So we think if we play here, we're going to win 75% of the time. But that's the best we got, so we're going for it, and then we won the game. That's it. So is this thing very accurate? No. Does it beat the simple AI of playing randomly quite a lot? Yes. Your homework will be to basically take this and make it a little bit better. So that'll be the next homework project. I'll give you guys the code, and the code is very similar to the final project code. So anything you learn in here will help you in the final project. There's 2 ways you can imagine making it better. You could try to play against a better AI, right? So better than just random. You can also play yourself. If you get better at playing yourself, then you can kind of get into a spiral where you get better and better, and then your opponent gets better and better. Then you just like learn and learn. You can get more accurate. There's all sorts of tricks you can do to make the value function more complicated or better, and that's what we're going to sort of do for the next couple of weeks in the course. It's like more and more tricks. This is like the basics of how your final project will learn, but we're going to like beef it up a little bit and learn some cool stuff as we go. Okay, I think that is everything I wanted to say for today. Any questions or comments? Okay, let's stop there then. And I'll see you guys on Tuesday.